Assalamu alaikum warahmatullahi wabarakatuh. Student, in this video we will discuss lab number 8 and lab number 9. In lab number 8, the objective is to analyze the response of a control system to ramp and arbitrary input signal. Basically, this topic is inconsistent with the topic of steady state error and error analysis, where we discuss the system types. We have different types of systems with respect to the number of poles at origin. If we have 0 poles at origin, means the system type is 0. If we have 1 pole at origin, means system type is 1, and so on. With this type of system, if we apply the variety of input, then what would be the system steady state error? Suppose in this case, if we have a type 0 system and we apply a step input, then system will produce a constant error. And if we apply a ramp input to the type 0 system, the system which has no pole or 0 pole at origin, the system will produce an infinite error. Same be the case for a parabolic input. For other type of system, this table is summarizing the steady state error accordingly. So here similarly we can observe the system response to the ramp input inconsistent with this table. Okay, now here we go. We have a type 0 system because here we cannot take a common S from the denominator, so we have no pole at origin. For analyzing the system response, we can use MATLAB. Here I have already written a program for analyzing the system. In this program, first of all, we have defined the transfer function of the given system. Here we have in the numerator a constant 30, so this can be written as 0 0 30. This 30 with s of power 0, this 0 with s of power 1, and this 0 with s of power 2. For denominator, we have s square plus 5s plus 6, so this denominator can be written in MATLAB as 156. Here this 6 with s of power 0, 5 with s of power 1, and 1 with s of power 0, means s square plus 5s plus 6. Okay, if I run this program and using step execution, after reading N, D, and after executing system, this command system is equal to TF. TF stands for transfer function with respect to the given numerator and denominator. We can see the transfer function in the command window after execution, because I have deliberately avoided to insert a semicolon here. So after execution of this command, we would be able to see the execution result in the command window as well. In order to observe the different time responses, like step ramp or parabolic response, or maybe any other input, I have used here LSIM command. In LSIM command, we have to define certain thing before the execution of LSIM command. First is the system. We have to define our system as we have defined earlier. Second is the input what input we want to give in. And next one is the time, at what time we have to check our time response. So here I have defined the time instant from 0 to 10 with a small increment of 0.01. Next, I want to use the step input in order to observe the step response. I have used this line number 11, which represents the step input. Therefore, when this particular line is executed, it will produce 1 up to this size t, which is already defined earlier. Okay, next is the command LSIM. We have already defined the system, the input u, the step input. We have 1 up to the time instant, and this is the time from 0 to 10 seconds. Okay, when this command is executed, it will return y, the system response, and the time t. Okay, next, if we want to check what we have in the workspace, we have time t from 0 to 10 seconds, as well as the system output response with respect to the time. After getting the output response with respect to time, now I am going to plot this response with respect to time. This array is used to define the x and y axis. The x, I want to have the x axis from 0 to 10 unit, and y axis is also from 0 to 10 unit, and axis v command will restrict the x and y axis with respect to given instruction here. Okay, now I'm going to plot the output u with respect to time. So here, with respect to time up to 10 unit, the value of the input is 1, which is defining the step input. Next is we have restricted the axis from 0 to 10 for x-axis and 0 to 10 for y-axis. We can also check here the x-axis is restricted to 0 to 10 value, as well as the y-axis. The Holden command is used to have another plot on the same figure, and we want next to plot response y with respect to time, and the color of this response should be with red color. So next is the plot of output response y. We can also check here when we have given the step input to a type 0 system, we have a constant error, and this is inconsistent with the theory we have discussed earlier. For a type 0 system, if we apply the step input, the system will produce a constant error, which is about r over 1 plus k. Okay, next are the cosmetic of this plot. The grid command is used to apply the grid on the same figure. The title command apply the title on the top of the figure. X level is time and the y level is amplitude. Okay, we have executed all command at once, and we can see all these things in the figure as well. The x is labeled as time, the y is now labeled as amplitude, and we have a title as well. So this plot is inconsistent with the theory we have discussed earlier. Next is, if we want to observe the ramp response, then comment this line. We do not need this input. We need a step input for this case, sorry, ramp input for this case. Here we have 1 multiplied with time, and time is this. Therefore up to then that instant we have a ramp input. Okay, now execute again this program. When we have executed LCM, we have restricted our x and y axis, and when we plot this command, we have to plot this command will plot input with respect to time. Therefore we have a ramp input. Next command we have discussed earlier. When I am going to execute all the command, we have the ramp response is the ramp input and is the output response of a type 0 system. And what we can observe here, the distance between these two lines are increasing. As the time increases, means the error is going to infinity, and this result is inconsistent with this table. For a type 0 system, if we apply a ramp input, then the steady state error would be infinity. If we want to observe the parabolic response, then once again we have to comment this line, because we do not require this input, we require the parabolic input. Therefore here is the parabolic input, t square. I am going to square all time instance. Okay, again run this program, define time instant, define input. Next execute the LCM command. We have defined earlier the system, the input and time. We have restricted the x and y axis using this command. Here is the plot of the parabolic input. Here is the restriction on x and y axis. Therefore we can see also in this figure. And then I am going to plot output response with respect to time with a red color. Okay, and grade the title and x and y length. Okay, here is the output response. In order to observe the value of the steady state response, here it is infinity when the parabolic input is given to type 0 system. If we want to realize this results more clearly, we have to redefine our x and y axis. Here I am redefining the y axis from 10 to 250 units. Once again I am executing the same program, and we have this curve is the parabolic input, is the output response, and here you can observe that these two lines are going away and away from each other, means the system is not following its input signal. Therefore it would produce therefore the error is increasing as time is increases, the error is also increases, and this is inconsistent with this table. For a time 0 system, if the input is parabolic, then the error would be infinity. Dear student, in this program we have discussed how a system can be defined, by defining the numerator and denominator and using the TF command. TF stands for transfer function. Next, we have also learned about the different type of input, how these input can be generated, like the step input using this command once with size of t. Second is the ramp input, and third one is the parabolic input. How these input can be generated. Next is the LCM command is used to obtain the output response with respect to time slot we have defined earlier in this program. So in this command we have to define these parameters earlier: the system, the input, and the time slot. Next is the next all instructions are pertaining to the cosmetic of the output response figure. Here we have also validated the theory we have discussed for the steady state error analysis. If we have a type 0 system and we are going to apply the step input, ramp input, and the parabolic input, then what would be the system response? And we have observed that the output responses for these three input are inconsistent with this table. For a type 0 system, a step input will generate a constant error, the ramp input will produce an infinite error. Same be the case for a parabolic input. In this way, we have completed task number 1. For the given type 0 system, we have applied not only the ramp input but the step and parabolic input as well. Instead of using a step input, I have applied here the LCM command for using different input signals. The next task is to apply an exponential input for this specific given time slot in a step of 0.15 second. The same program which we have written earlier for step, ramp, and parabolic input can be used for exponential input as well. Here is the program for task 2. In task 2, first of all, we have to define the numerator. The numerator is 5 with s of power 0 and 1 with s of power 1, means s plus 5 in the numerator, as we have given in the given transfer function. In the denominator we have s cube plus 2s square plus 3s plus 5, means 1, 2, 3 and 5. Okay. 1, 2, 3 and 5. 1, 2, 3 and 5 we have to place here in order to define the denominator. The time slot is given is from 0 to 9 seconds with a step size of 0.15. Next is the command is used to define the exponential input minus 0.2 into t. This exponent is raised to the power of minus 0.2 t as given in our lab manual. Okay, then we have to write down further instruction in order to get the response. Y is equal to LCM. We have to define here the system is defined with numerator comma denominator, or we can also use here system command as we did in the program written for step, ramp, and parabolic input. It is the alternate way to apply the LCM command and to define the system. Here R is used to define the input, T is used to define the time slot, then plot command is used to plot the input R with dashes, and to plot y with circles. Okay, now here I am going to plot the output response with respect to the exponential input. Okay, fine. Okay, student, next the task is given to you. For this particular system, which is a type 0 system, and you have to apply this input using LCM command from time 0 to 15 seconds in a step size of 0.001. Thank you very much. Students, now come to the lab session number 9. The objective is to learn the command in MATLAB that would be used to reduce a linear system block diagram using series, parallel and feedback configuration. We have also studied in our theories session about the block diagram reduction technique. If we have the block in cascaded and parallel or in a feedback configuration, then how this block could be reduced and to represent with the help of a single block. So here we are going to repeat all this theory content. Number one is the series configuration. In this series configuration, system 1 and system 2 are in series. These two systems are defined with the help of the transfer function G1s and G2s. In order to get the equivalent of these two blocks, we have to use a MATLAB command series. In this series command, we have to define system 1 and system 2 in order to get its equivalent transfer function. Here in the MATLAB program, we have defined system 1, the transfer function of first block, by defining the num1 and denominator 1. Now I am going to run this program in a step. Here is the execution of num1 and denominator 1. By using this command, we are able to define the transfer function of the system 1. The absence of semicolon means we can see the transfer function in the command window is 1 by s square, as I have discussed earlier. The next is the transfer function of system 2. 1 means s plus 1 and 1 2 so power 0, so power 1 means s plus 2. If I am executing these two commands, this will give the system 2 as well, and we can also see in the command window. So I have defined the system 1 and system 2, and here in this diagram these two systems are in series. Okay, now I am going to execute this command. This will give us the equivalent of the series configuration. Okay, now here we can see the equivalent of the cascaded system. So this series system can be represented by a single block with this transfer function with input u and output ys. Okay, now next is the parallel configuration. In this parallel configuration, once again we have two systems. These two systems are added together. If we want to eliminate this parallel configuration and want to replace by a single block, then we have to use a parallel command similar to the series command. Okay, here is the coding for the elimination of a parallel block. System 1 and system 2 are defined earlier. After the execution of this command, the system 1 2 is the equivalent transfer function of the parallel block. Okay, now here we go. We can see the system 1, 2. Here is the equivalent transfer function of the parallel block. Next one is the feedback configuration. In feedback configuration, we have two cases. First one is for unity feedback control system, and other one is for non-unity feedback system. If we have a unity feedback system, here the value of HS is 1. We are able to eliminate this feedback loop, and we can represent a unity feedback system by a single block by finding its equivalent transfer function. This equivalent transfer function can be obtained by using this command, feedback, and we have to define the system 1. System 1 is the transfer function of the forward block. The value of the feedback element HS is 1, and the sign here, the plus minus sign here, is used to represent a positive or a negative feedback system. Okay, we can also see in the MATLAB program as well, the feedback command is used to find out the equivalent of a feedback configuration. System 1 is the transfer function of the forward block. Okay, now execute this command. This will give us the transfer function of a unity feedback system. Here it is. This one is for unity feedback system, and -1 is for negative feedback system. After the execution of this command, where we can get the equivalent of a unity feedback system, and this value is stored in system_2. Here is the equivalent transfer function of a unity feedback system. For a non-unity feedback system, first of all, we have to define the transfer function of forward element, the transfer function of the feedback element. Then by using the feedback command, we have to define the system 1, the transfer function of the forward element, the transfer function of the feedback element, and we can also write down here -1 for negative feedback system. If we are not using -1 here, then by default this command is assuming the negative feedback control system. If I am executing this command, we can see the equivalent transfer function of a non-unity feedback system in the command window. Okay, now come to the task number 1. The task number 1 is to develop the equivalent transfer function of the series configuration, and we already did it in the MATLAB program using a series command. First of all, we have defined the transfer function of the first block, the transfer function of the second block, and this series command give us the equivalent transfer function, and we have also seen in the command window as well. The next task is to develop the equivalent transfer function of the unity feedback configuration. First of all, we have defined the transfer function of the system 1, this transfer function is system 2, then series command is used to find out the equivalent transfer function of the series configuration, then feedback command is used to find out the equivalent transfer function of the entire given configuration. This system 3 is the equivalent transfer function of the series configuration. This one is for unity feedback, and this feedback command is used to find out its equivalent, and we have already did in our MATLAB program as well, and we have also seen the outcome of this command as well in the command window. The next one, task 3, is to eliminate the non-unity feedback configuration. We have already did in our MATLAB program. We have defined system 1, the system 2, and -1 is used to define the negative feedback system. We have already did this task number 3 as well. Next is the task number 4. It is pertaining to plot the location of system zeros and poles using MATLAB code. Here is the information about the system. The numerator is s square plus 1, and the denominator is pertaining to x cube plus 3s square plus 3s plus 1. By using this command, system G is equal to TF with defined numerator and denominator. This will give the polynomial form of the transfer function, and this command 0 under bracket the defined system G will give us the zeros of the given system. Same be the case for this command, poles under bracket system G. This will give us the information about the system pole. Okay, now here we go. Here is the MATLAB code for task number 4. N1 is representing the numerator of a given system, D1 is representing the denominator. The numerator has 6s square plus 1, the denominator has s cube plus 3s square plus 3s plus 1. When I am going to execute this command, this will give us the system 4 in polynomial form like this, as I have told you earlier. When I am going to execute the 0 command and the pole command, this will give us the pole and zeros of the given system. Here is the code for performing task number 4. N1 is the numerator of a given system, D1 is the denominator of the given system. In the numerator we have 6x square plus 1. In the denominator we have s cube plus 3s square plus 3s plus 1. When I am going to execute this code at line number 25, this will give us the transfer function in polynomial form in the command window. Here we can see this. When I am executing the 0 and pole command, this will give us the location of pole and zeros. If I intend to map the pole and zero location in sigma and j omega plane, then simply write down MATLAB command tz map of for the system _4. This will give us the pole zero location in sigma j omega plane. These poles cross is representing system pole. The poles are at -1. The system zeros are at 0 and 0 plus 4 0.40 at 2 iota. Okay. Next is the problem is given to find out the pole zero location for this particular system. In this system we have two terms in the numerator, two polynomials in the numerator and three polynomials in the denominator. So first of all we have to simplify the two terms in the numerator and the three terms in the denominator by using a convolution conv command. Okay, here is the MATLAB code. We have one term s plus 1, second term s plus 2. These are two terms in the numerator. Then by using this convolution command, by defining n1 and n2, these are two terms in the numerator. We can find out the equivalent term in the numerator with this num. Okay, now going to execute this command. Here in the command window we can find out capital num is 132 instead of s plus 1 and s plus 2. Next one is the same with the case for the denominator. This denominator has three terms. The first one is s plus 2 iota, the second term s minus 2 iota, the third term is s plus 3. And by using this command d1 and convolution of d2 d3, first of all we have to multiply these two terms and then multiply d1 with this term. This will give us the equivalent term in the denominator. We can also view the denominator den, how I have defined in the okay. Still I haven't executed this term, so first of all I have to execute this term, then find out den here. This would be s cube plus 3s square plus 4s and plus 12. Okay, fine. Next is to find out the transfer function of the given system. Okay, after the execution of this term we would be able to see the equivalent transfer function in polynomial form in the command window. Finally, if you want to look at the pole and zero in sigma and j omega plane, then simply execute this code. This will give us the pole zero location of system underscore 5. Here is the pole zero map. One pole is at -3, the 0 is at -2, the next 0 is at -1, and these are the two poles. One is at 0 and plus 2 iota and 0 minus 2 iota. Finally, you have to write down your conclusion, what you have learned in this lab, and you have to do one exercise. You have to find out the equivalent transfer function ys over xs for the given system. You have to simplify the block diagram by using series, parallel and feedback command. These are the transfer function of all individual blocks, and this is up to you to solve this exercise appropriately. As a hint, you may combine these two blocks, and after combining these two blocks and finding the equivalent transfer function, the equivalent block and these two blocks will be added together by using a parallel command. And same be the case for other blocks. With respect to theory, we have discussed in this lab number 9. Here it is all from this lab number 5, lab number 9. Thank you very much.